Download this code from codegive.com, link in the description below. Dynamic memory allocation in C, a comprehensive tutorial. Dynamic memory allocation is a powerful feature in C that allows you to allocate memory during runtime. This is essential for scenarios where you don't know the size of the memory you need at compile time, such as when working with user input, variable length data structures, or large data sets. This tutorial will cover the concepts, functions, best practices, and common pitfalls associated with dynamic memory allocation in C, providing detailed explanations and code examples. 1. Why dynamic memory allocation? In C, you can allocate memory in two primary ways. Static allocation. Memory is allocated at compile time. This includes global variables, static variables, and local variables declared inside functions. The size and lifetime of these variables are known during compilation. Dynamic allocation. Memory is allocated at runtime using functions like malloc, calloc, realloc, and free. The size and lifetime of the allocated memory are determined during program execution. Here's why dynamic allocation is often preferred. Flexibility. You can request memory based on user input, file sizes, or other runtime conditions. You're not restricted to predefined sizes. Efficiency. You allocate only the memory you need, avoiding wasted space. You can also release memory when it's no longer required, preventing memory leaks. Data structures. Dynamic allocation is fundamental for implementing dynamic data structures like linked lists, trees, and graphs, where the size can grow or shrink during execution. Passing data between functions. When you need to pass a large data structure created in one function to another, dynamically allocating memory and passing a pointer is often the most efficient and preferred method. 2. The standard library functions, stlib.h. The stlib.h header file in C provides the core functions for dynamic memory allocation. Malloc, memory allocation. Prototype void malloc, size_t size. Purpose allocates a block of memory of the specified size, in bytes. Return value returns a pointer to the beginning of the allocated memory block. If the allocation fails, example due to insufficient memory, it returns null. The pointer returned is a void which means it is a generic pointer that needs to be cast into appropriate data type before use. Initialization malloc does not initialize the allocated memory. The contents of the allocated block are undefined, garbage. Example calloc, contiguous allocation. Prototype void calloc, size_t mem, size_t size. Purpose allocates a block of memory for an array of mem elements, each of size bytes. Crucially, calloc initializes the allocated memory to 0, all bits set to 0. Return value returns a pointer to the beginning of the allocated memory block. If allocation fails, it returns null. Initialization calloc initializes all bytes in the allocated memory to 0. Example realloc, reallocation. Prototype void realloc, void ptr, size_t size. Purpose resizes a previously allocated block of memory pointed to by ptr to a new size. Return value returns a pointer to the reallocated memory block. The pointer might be the same as the original PTR if the memory could be resized in place. If a new block is allocated, because the original block couldn't be expanded, the contents of the original block are copied to the new block. If reallocation fails, example due to insufficient memory, it returns null. The original PTR remains valid in this case, but you should not use its data as the data is likely to be undefined. Asterisk important asterisk. Asterisk if PTR is null, realloc is equivalent to malloc size. Asterisk if size is 0, realloc is equivalent to free PTR and returns null. Asterisk if the reallocation requires moving the data to a new memory location, the original memory is automatically freed. Therefore, never use the original pointer, PTR, after calling realloc, regardless of whether the reallocation succeeded or failed, unless realloc returned null, in which case PTR remains valid but shouldn't be assumed to contain valid data. Asterisk example asterisk. Asterisk free, deal location. Asterisk prototype asterisk void free, void asterisk PTR. Asterisk purpose asterisk releases the block of memory previously allocated by malloc, calloc, or realloc. Asterisk argument asterisk takes a pointer PTR to the memory block to be freed. PTR must be a pointer that was previously returned by one of the allocation functions. Passing an invalid pointer, example a pointer to a static variable, a pointer that has already been freed, or a pointer that was not obtained from a memory allocation function, leads to undefined behavior, often a crash. Asterisk important asterisk. Asterisk it is crucial to free memory when you are finished with it to prevent memory leaks. Asterisk after free PTR, the value of PTR itself is unchanged. It's a good practice to set PTR equals null after freeing it to avoid accidentally using the dangling pointer. Asterisk freeing the same memory block multiple times results in undefined behavior, usually a crash. Asterisk free, null, is safe and does nothing. Asterisk example asterisk, see the examples above for usage within a complete program. 3. Common mistakes and best practices asterisk asterisk. Asterisk memory leaks asterisk failing to free allocated memory when it is no longer needed is a common cause of memory leaks. Over time, a program with memory leaks can consume all available memory, leading to crashes or performance degradation. Asterisk dangling pointers asterisk using a pointer after the memory it points to has been free, d. This can lead to unpredictable behavior, as the memory may have been reallocated to a different part of the program or overwritten by other data. Always set the pointer to null after freeing the memory. Asterisk double free asterisk attempting to free the same block of memory more than once. This leads to undefined behavior and often a crash. Asterisk invalid pointer to free, asterisk passing a pointer to free that was not obtained from malloc, calloc, or realloc, or a pointer that has already been freed. Asterisk accessing memory out of bounds asterisk writing or reading data beyond the allocated size of a memory block. This can overwrite other data in memory, leading to unpredictable behavior and crashes. Asterisk not checking for null returns asterisk always check the return value of malloc, calloc, and realloc, to ensure that memory allocation was successful. If the allocation fails, these functions return null. Failing to check for null can lead to a program attempting to dereference a null pointer, resulting in a crash. Asterisk incorrect size calculations asterisk when allocating memory for arrays or structures, be sure to use size of to calculate the correct size in bytes. Make sure to multiply by the number of elements when allocating memory for an array. Asterisk forgetting to cast the return value asterisk the allocation functions, malloc, calloc, realloc, return a void asterisk which is a generic pointer. You need to cast this pointer to the appropriate data type for the memory you are allocating, example int asterisk, malloc, size of, int, asterisk 10. Although some older C compilers might allow assignment without a cast, it's best practice, and required in C++, to always cast the return value for type safety and to avoid compiler warnings. Example demonstrating common mistakes and solutions asterisk. 4. Dynamic memory allocation for data structures asterisk asterisk. Dynamic memory allocation is essential for creating dynamic data structures like linked lists, trees, and graphs. Here's a simple example of a linked list node. Explanation of the linked list example asterisk. One struct node asterisk defines the structure of a linked list node, containing an integer data and a pointer next to the next node in the list. 2 create node, asterisk allocates memory for a new node using malloc, initializes the data field, sets the next pointer to null, and returns a pointer to the new node. Critically, it checks if malloc was successful. 3 insert node, asterisk inserts a new node at the beginning of the linked list. It takes a pointer to the head of the list, passed by reference node head, so that it can modify the head pointer if the list is empty. 4 printy list, asterisk traverses the linked list and prints the data of each node. 5 free list, asterisk frees all the memory allocated for the linked list nodes. This is essential to prevent memory leaks. It iterates through the list, freeing each node one by one. It's important to store the next pointer before freeing the current node to avoid losing the reference to the rest of the list. 5. Using valgrind to detect memory errors, Linux/Mac OS. Valgrind is a powerful memory debugging tool available on Linux and Mac OS systems. It can help you identify memory leaks, invalid memory access, and other memory-related errors. Asterisk installation asterisk install valgrind using your system's package manager, example sudo apt-get install valgrind on Debian/Ubuntu, brew install valgrind on Mac OS with Homebrew. Asterisk usage asterisk run your program under valgrind's memc tool. Asterisk interpreting the output asterisk valgrind's output will report any memory errors it detects, including asterisk memory leaks asterisk blocks of memory that were allocated but not freed. Asterisk invalid reads/writes asterisk accessing memory outside the bounds of an allocated block. Asterisk use of uninitialized values asterisk using the value of a variable that has not been initialized. Asterisk double freeze/invalid freeze asterisk attempting to free the same memory block multiple times or passing an invalid pointer to free. Example valgrind output, showing a memory leak. The output indicates that 40 bytes were definitely lost, meaning that the program allocated memory but never freed it. The output also provides the line number in the source code where the memory was allocated, leak \example.c6, making it easy to track down and fix the leak. 6. Dynamic memory allocation with struct s and unions ***. Dynamic memory allocation is particularly useful when working with structures and unions, especially when you need to create arrays of structures or dynamically allocate memory for structure members. Explanation ***. One person structure * defines a structure person containing a character pointer name and an integer age. The name member is a pointer to a dynamically allocated string. 2 dynamic array of structures * the program prompts the user for the number of people and then allocates memory for an array of person structures using malloc. 3 dynamic memory for strings * inside the loop. The program reads the name of each person using fgets, to safely handle spaces in the name. It then dynamically allocates memory for the name string using malloc, and copies the name into the allocated memory using strcpy. For memory management *, the program carefully frees all allocated memory, including the memory for the names and the memory for the array of person structures. Important considerations for struct *. Nested dynamic allocation * structures can contain pointers to dynamically allocated memory. It's your responsibility to manage the memory pointed to by these pointers. Order of deal location * when freeing a structure with dynamically allocated members, you must free the members before freeing the structure itself. As shown in the example. Copying structures * when copying a structure containing pointers to dynamically allocated memory, you typically need to perform a deep copy to allocate new memory for the pointed to data. A simple assignment, shallow copy, will only copy the pointers, leading to potential issues with shared memory and double freeze. 7. Conclusion *. Dynamic memory allocation is a crucial tool for writing flexible and efficient C programs. By understanding the functions malloc, calloc, realloc, and free, along with the best practices and potential pitfalls, you can effectively manage memory in your programs and avoid common memory-related errors. Remember to always check for null returns from allocation functions, free memory when you're done with it, and be careful when using pointers to dynamically allocated memory. Using tools like valgrind can significantly aid in detecting memory errors during development. Good luck.